So now you can start.
Okay, thank you. Good morning, good afternoon, and good evening to all. I'm Suchithra Sundaram, one of the conveners of this session on polar climate variability, teleconnections, global monsoon, past, present, and future. I worked as a research associate at New York University, Abu Dhabi, and my research interests are polar climate variability, teleconnections, Asian monsoon, and paleoclimate modeling. So on behalf of SCAR 2022 and behalf of the conveners of this session, I extend a warm welcome to all the speakers, e-poster presenters and attendees. For today's session, we have 9 speakers and 3 e-poster presentations. The e-posters can be viewed throughout the conference, and we are glad that we got speakers from almost all over the globe. And as the session will progress, then you will notice that the session covers many of the topics that are relevant to the rapid changes observed over the polar regions. Some of the topics that are related to this session is the teleconnections between the ocean atmosphere coupled phenomenon and the polar regions, the impact of northern and southern annular mode, then the rare events like the polynyas, the least explored research topic, the teleconnection between the Asian monsoon and polar region. Then there are talks which stress on the anthropogenic forcings, and there are also talks which mention about the impact of internal variability of the climate system on the polar regions. Then there are field observation studies, then climate modeling studies, then analysis of observation, satellite and reanalysis data sets, and many more. Only one thing we lack here is that there is no paleoclimate speakers for this session. And this session is convened by myself, then Dr. Deepa, Ravindran Pillai from Florida Agricultural and Mechanical University in US, and then Dr. Sourav from Sourav Chatterjee from National Center for Polar and Ocean Research in India. And for the smooth functioning of the program, we request the speakers to try to manage to complete the presentations within the 10 minutes and spend 2 minutes for question and answers. The attendees can send the questions through the chat box, and the speakers will answer 1 or 2 questions during the presentations, and the others they will answer during the discussion session, which is kept at the end of the session. And those questions which are unanswered due to the unavailability of the time will be sent directly to the respective speakers. And also attendees can directly contact the speakers for the questions. So once again, I welcome all of you, and I wish and hope that we will have a lively and highly interactive session. So the first talk of this session is by Professor Matt King. He's a professor at University of Tasmania, the director of Australian Center for Excellence in Antarctic Science. His research fields are geodesy, ice sheet changes, sea level changes, and solid earth deformation. And the title of the talk is Climate Variability as a Major Forcing of Recent Antarctic Ice Mass Change. So it's a pre-recorded talk, so you can start that now.
Well, hi, and I'm here to talk about some of the work we've been doing on understanding ice mass change and its variation over time, and how that relates to large-scale modes of climate variability. Well, hi, and I'm here to talk about some of the work we've been doing on understanding ice mass change and its variation over time, and how that relates to large-scale modes of climate variability. And this is work undertaken with Kui Liu and Shibin Zhang. And we really start with a dilemma because the southern annular mode hasn't been detected in geodetic time series of Antarctic ice sheet mass change. Groups have looked at specific ENSO events and correlated ENSO indices with mass change events in Grace time series, but SAM hasn't been detected despite groups looking for it. And that's odd because we know that SAM, an increasing positive SAM, is related to a reduction in precipitation. For example, the work of Medley and Thomas, where we see their reconstructed accumulation trends over 1957 to 2000 on the left-hand side, and the SAM congruent component of that trend, or those trends, on the right-hand side. And we can see that SAM is associated with substantial variability, both in terms of spatial patterns of it, but also that sustained trends over that. Well, studies. We really start with a dilemma because the southern annular mode hasn't been detected in geodetic time series of Antarctic ice sheet mass change. Groups have looked at specific ENSO events and correlated ENSO indices with mass change events in Grace time series, but SAM hasn't been detected despite groups looking for it. And that's odd because we know that SAM, an increasing positive SAM, is related to a reduction in precipitation. For example, the work of Medley and Thomas, where we see their reconstructed accumulation trends over 1957 to 2000 on the left-hand side, and the SAM congruent component of that trend, or those trends, on the right-hand side. And we can see that SAM is associated with substantial variability, both in terms of spatial patterns of it, but also that sustained trends over that multi-decadal periods. We also know, based on ocean modelling, that SAM alters the heat transport in the ocean to ice shelves, and hence it forces ice shelf melt, potentially affecting upstream ice discharge. So we should see, at very least, the atmospheric component of SAM in Grace time series. So where is it? Well, studies have tended to compare Grace mass time series with the raw SAM and ENSO indices, and here on the figure I've shown the SAM Marshall index normalized and the Nino 3.4 ENSO index, and you can see their temporal patterns there, and these are generally related to the flux of moisture and heat. But Grace and altimetry over the ice sheet, they're sensitive to mass, not mass flux. Paolo and others looking at ice shelf altimetry, and Kim and others looking at surface mass balance data have also identified that we shouldn't be looking at the raw indices, we should be looking at the cumulative indices. And so now if we accumulate these indices in the top panel, we get what we get in the middle panel, now dominant decadal variability in the Nino 3.4 sigma series, and the SAM sigma series, a substantial trend as SAM shifts towards the positive phase. If you detrend that in the bottom panel, you see this decadal variability in addition to the existence of that linear trend. And that linear trend is important. We'll come back to that in a minute. Now, if we do an EOF analysis of the detrended Grace and Grace follow-on data, well, it shows dominant decadal signals as well. Here's the dominant mode and its principal component with that decadal signal. The second mode, large-scale coherent spatial patterns as well, and again, a decadal variability of some kind. Now, if we overlay with that, the detrended SAM sigma and over PC1, we see very strong correlation, something around 0.72, and the Grace PC2 correlating with the detrended Nino 3.4 sigma series. In particular, strong correlation above 0.8 when you include a lag of about half a year. So SAM and ENSO seem to be present in Grace data, but we need to be treating it with the cumulative sum of the indices, not the indices. Now, if we take those principal components and regress against them the RACMO surface mass balance model, we get spatial patterns that are very similar to the dominant modes of variability in detrended Grace data. Not exactly the same signal, but very similar, suggesting that the surface mass balance is a major component, not necessarily the whole component, of this decadal variability we're seeing in Grace data for both SAM and ENSO. So that encouraged us enough to want to look further into this. So we did a multivariate regression, including a linear term, some periodic terms, and these SAM sigma and Nino 3.4 sigma terms. And here is the estimated SAM coefficient when we regress those terms against the Grace time series, now with the trends included. And so we get large-scale coherent spatial patterns with strong signal in the Amundsen coast and around to Murray Birdland and through to the southern Antarctic Peninsula. Similar responses from just around the Totten Glacier through to the West Ice Shelf. Opposite signals in Droning Maudland, Eastern Wilkes Land, and the northern Antarctic Peninsula. The ENSO signal shows this bimodal distribution of one sign of signal in through the Antarctic Peninsula, through to the Amundsen Sea and the Murray Birdland, and right through to the Eastern Wilkes Land, and an opposite signal through much of the rest of coastal East Antarctica. Now, if we take just those two terms, now remembering that the SAM sigma coefficient has a linear component to it, if we take those two terms and compute the percentage of variance explained by those two terms, well, we get values that are up around the 60 to 80% and even above that around coastal East Antarctica. If we remove the trend out of the SAM sigma coefficient, we're still sitting at around the 60%. So these two terms alone can explain at least 60% of the variance of much of the vulnerable sectors of coastal East Antarctica, West Antarctica, and the Antarctic Peninsula. And if we want to dig into that a little bit more, now we're showing with the blue dots time series of mass change after we've removed the estimated linear component. Now there's still a trend-like component in here that's associated with SAM. And so we can see here in the top left the full Antarctic ice sheet with the ENSO model in the purple. Not much ENSO signal in Antarctica overall because it cancels in between regions. The SAM signal basically dominates the model for the full ice sheet. If you look though at the Antarctic Peninsula ice sheet, you see that ENSO is dominating here, and this model does a really nice job of replicating the Grace time series after the removal of that linear trend, and not much SAM signal here overall because some of the signals cancelled in the northern and southern sections. Similar story in East Antarctica. And in West Antarctica, we have a little bit of ENSO signal, but dominated by the response to SAM sigma in these regions. Now we can dig down even further into smaller basins. This is the Thwaites Glacier Basin here, Pine Island, Bellingshausen Sea, the southern Antarctic Peninsula, and the northern Antarctic Peninsula. And you can see that these two terms are doing a pretty nice job at explaining the time series of Grace and its sort of decadal scale variability with the consequent trend-like component associated with SAM. So let me just go through that part of it again. So you'll recall that SAM sigma has to have a trend in it because SAM is trending towards the positive. And so when we take this SAM sigma coefficient from the regression, and it will effectively be multiplied by this trend. And so we will get trends across the ice sheet associated with the SAM sigma, and we'll get negative trends in West Antarctica through to the Southern Antarctic Peninsula, negative trends in the region of Totten Glacier through to the West Ice Shelf, and opposite side trends in other regions. And so this shift to SAM, positive SAM, actually, when we compare the straight linear terms that we estimate from a linear regression, including those terms, we get negative 90 gigatons a year from Antarctica. If we leave those out, we get negative 160 gigatons a year. So basically, SAM and ENSO, in particular SAM, is explaining about 68 gigatons a year over this period. And if you look at the ice sheets overall, over all the Antarctic Peninsula ice sheet, not much effect overall. If you break it down to smaller regions, there's a bigger effect. Similar story for East Antarctica, and it's really all about West Antarctica, where almost 50% of the long-term trend in this region can be explained by SAM. And that's my story that I wanted to tell today.
Thank you, Professor Matt. I can't find any question at present. So we'll move to the next session. And if any other question is there, we will discuss at the end of the session. Okay, bye. So next speaker is Dr. Sang-Yoon Jun, and he's a senior research scientist at the Unit of Sea Ice Prediction at Korea Polar Research Institute. His research interests are paleoclimate modeling and ocean atmosphere sea ice interaction studies. So can you please play Sang-Yoon's presentation?
Hello everyone, my name is Sang-Yoon Jun, the researcher from Korea Polar Research Institute. So first of all, thanks for allowing introduce our research result. In these presentations, I will share our result titled Internal Origin of the West-East Asymmetry of Antarctic Climate Change. This one was conducted with this collaborator and was already published in Science Advances in 2020. Two polar regions have experienced different climate change under global warming. This map by NASA's Goddard Institute for Space Studies shows Earth's average global temperature from 2013 to 2017 as compared to a baseline from the 1951 to 1980. The yellow, orange, red shows regions warmer than the baseline. The contrasting to substantial warming, so over the whole Arctic region, the asymmetry, the change of surface temperature was found over the Antarctic region. The change in cryosphere was also found consistently with these different climate changes. The sea ice over the Arctic has been melted over whole Arctic regions, but the volume loss from the ice shelves only found in the West Antarctica region. The long-term trend from the surface temperature reconstruction by Deacon Greenwich and HEDWSSD1 dataset clearly shows the asymmetric climate change over West and East Antarctica. Substantial increase in surface temperature and sea surface temperature was found on west side of Antarctica. However, it's hard to observe the substantial warming in East Antarctica, and even cooling was found of the ocean along east side of Antarctica. To find the reading patterns in Antarctic surface climate change, we applied the UFO analysis to the annual mean surface temperature of Antarctica from Nicholas and Bromwich dataset. The UFO analysis yield the first UFO mode representing the single science variability over the entire continent with explained variance of about 48%, and the secondary UFO mode representing the seesaw pattern with its node along the Transantarctic mountains with explained variance of about 20%. Corresponding principal component, the present common increasing trend, so both UF2PC has more pronounced multi-decadal fluctuations in the trend. In the concurrent positive phase of these two modes, West Antarctica, they experienced the substantial warming by reinforced these two modes, while over East Antarctica, the opposite sign, the variability in two mode with weak warming, namely the reading mode from UF analysis can explain the recent feature of Antarctic surface temperature change. Seasonality is key to understanding the mechanism behind Antarctic climate change. The first two European modes from seasonal mean surface temperatures are consistent with those from the annual mean surface temperature. Especially the UF2 PC of annual mean surface temperature has the largest correlation with from winter, is red bar, and west-east surface difference, the green bars, and the relative 300 hectopascal geopotential height average over the West Antarctic region, so also largest during the winter. Thus, it is concluded that UF2 is the mode that amplified in Austral winter, so forming the west-east surface asymmetry in Antarctic climate change. The climate model simulations are valuable for complementing observational efficiency of Antarctica. Thus, we examine the widely used model data from the coupled model intercomparison project, page 5. The common basis function analysis reveals the two reading modes in the historical simulation of 38 SIMI5 models for the same period with the observation. And the physical and seasonal characteristics of the reading mode in the observations are well simulated by these SIMI5 models. So most SIMI5 models simulate to observed mode with the amplitude more than the 0.8. The marked near the amplitude with the value of 1 in the x-axis, so indicate that the model simulate the observed variability with almost the same intensity. The first mode, the robustly shows the increasing trend in the SIMI5 model, as it does in the observations. So, however, the second mode shows a weak negative trend in multi-model mean value in contrast to increasing trend in the observations. The strengthening of the first mode undergo warming in both observation and SIMI5 historical simulations suggest that this mode might be closely linked to the global temperature rise. To find robust evidence for the characteristic of two reading modes, we further analyze multiple data sets of long-term Antarctic surface temperatures. Surface temperature reconstructions for the last 2,000 years with ice core, the base Antarctic 2K, and two long-term paleoclimate result from the Middle Ocean, Cream and Trace, and 4 simulations for the 20th and 21st centuries by CSM1. Despite the diversity of these data sources, so all data sets consistently shows the first mode explaining the same change across entire Antarctic, and the second mode presenting the asymmetric change over Antarctica in their UFs. And the spectral analysis shows the second UF species have internal variability and multi-decadal variability in the data set longer than 1,000 years. The first species from all data sets reflect the long-term change in relatively post-global scale climate change, the gradual cooling, so from Middle Ocean to present, by Cream, and abrupt warming after long-term cooling trend, the shaped similar with hockey stick, during last 2 millennia, by page 2K, and sustained warming in historical and future simulations on the greenhouse gas increasing. However, so all of the second species do not display any trend reflecting global scale climate change. That is, all of these results strongly suggest that the first mode closely linked to the global scale climate change, while the second mode might be associated with the internal variability within the Antarctic environment. The fact that second mode consistently shows no relationship with external global scale position change in the diverse data set suggests that this variability could be manifested by climate factors in Antarctic and adjacent regions. The Antarctic topographical distinctions between the West and the East Antarctic ice sheet, divided by trans-Antarctic mountains, could be a major factor because it differentiates any influence on the Antarctic curve between the two ice sheet regions. Thus, we perform the sensitivity experiment on changing Antarctic terrains using a coupled model to demonstrate whether the topographical distinction is the key factor behind the asymmetric climbing mode. With the current Antarctic terrain, the coupled model produces the asymmetric mode similar to that observed in terms of spatial patterns. And the experiment with the flattened East Antarctic ice sheet shows the asymmetric mode becomes stronger with the expansion of the West Antarctic warm region farther toward East Antarctica. In contrast, the elevated West Antarctic ice sheet experiment produce the weak asymmetry with negligible West Antarctic warming. From this experiment, we can deduce the role of Antarctic the topographic layout in controlling the tropospheric circulation and consequent surface temperature of Antarctica. The current low to West Antarctic terrain allows warm air advected from the ocean to West Antarctica, while the steep transatlantic mountain prevent the warm air from flowing toward East Antarctica. Across these heated regions, the barotropic anticyclone system develops, which can reinforce warm air advection from the ocean. And this anticyclone system also enforces the southward meridional oceanic flow over the West Antarctic Sea by Ekman transport, which supplies warm air from the extratropics. Eventually, the warmer land surface and development of the anticyclone system and warmer ocean surface together strengthen the warming of the West Antarctica by promoting each other. The mutual cooperation of these factors can be confirmed in two altered terrain experiments. Okay, I'll summarize our result. We checked the variability of surface temperature between West Antarctica and East Antarctica from the recent near surface temperature reconstruction and the SIMI-5 historical simulations, the 2000 years temperature reconstruction based on ice core, and paleoclimate, the modern result with the two models. The Antarctic topography and atmosphere and ocean interactions of Western Antarctic coastal region might contribute to the asymmetric variability. So climate change in global scale does not seem to affect the variability, then rather affect temperature change over the entire Antarctic. The result suggests that the current west-east asymmetry, the surface climate change is of natural origin. That's all. Thank you for your attention.
Thank you, Sang-Yoon. So it was a nice presentation, and we have one question from Gennady Milensky. Do you consider impact of central tropical Pacific influence on Western Antarctica via teleconnections? Sang-Yoon, are you there? Okay, I think he's not there. So we will move to the next talk. So next talk is by Dr. Amita Prabhu. She's a senior scientist at Indian Institute of Tropical Meteorology, and her research interest includes polar teleconnections, then Asian monsoon dynamics. So Amita, please.
Thank you. Am I audible?
Yes, yes, yes.
Hello, everyone. I would be giving a talk on this topic, relationship between annular mode and its relationship with the regional aspects of summer monsoon rainfall over India. So basically, we are talking about the annular modes, both southern annular mode and the northern annular mode. So in this respect, how the southern annular mode would affect the major parts over India, while the northeast region, which is usually the rainfall patterns are just the opposite with the rest of the country. So what Northern Annular Mode has, or the Arctic Oscillation has got to do with it, that is exactly what we are going to see in the following slides. So Northeast India, basically we see that it's the most dominant mode of variability in summer monsoon rainfall. However, the pattern of the rainfall over Northeast India is opposite to that of the rainfall which we see for the rest of the country. Southern Annular Mode studies which have been done earlier shows that the climate variability over East Asia and the SAM, they are positively related, and the regions or the bridge that connects Southern Annular Mode to the rainfall over East Asia is through the Indian Ocean. So the motivation in this study is to investigate how the annular modes, both the Southern Annular Mode and the Northern Annular Mode, could decipher the opposite rainfall patterns over the Indian landmass and also over the Northeast India, and further to examine the physical relationship addressing this links. So we take NCEP-NCAR data for the period 1949 to 2013. When we see the correlation with Indian summer monsoon rainfall, it is insignificant. So we go ahead and see the interannual variability patterns for this period for mean sea level pressure at 40 south, 70 south, and the difference between the two, which is a SAM index between 40 and 70 south. So here what we see is that although the pattern, although the trend, there is no trend for the standardized mean sea level pressure at 40 degrees south, there's a decreasing trend which is evident, which is significant at 99% confidence level. And we see this coming from post-1980s. So this is attributed to increase in the greenhouse gases, to the increase in global mean temperature, and also due to ozone depletion. This is further seen by taking the annual cycles for the two periods, one for 1949 to 82, and the other period from 83 to 2013. There's a clear distinction between, although the seasonality is very well seen in both these periods, but there's a distinct difference in the magnitude of around 5 HPA. So henceforward, we concentrate on the period from 1980 onwards. So when we take a correlation between the Southern Annular Mode Index and the Indian summer monsoon rainfall index, we see for the bi-monthly SAM index, February-March SAM is correlated with the following JJS summer monsoon rainfall, the correlation being significant, positively significant. So although earlier for the entire data period, we didn't see any correlation coming up, but for post-1980s, we see there's a significant correlation. So when we take a spatial map of the two, we do see that an inverse correlation for major part of the country. So it is generally seen that when the rainfall is subdued over the Indian mainland, it is active over the equatorial region. This is contributed to the 30, 60 or the 40-day intra-seasonal oscillatory mode, which is prominent over the Indian longitudes during the summer monsoon season. Next, when we to see the mechanism through which this is possible, we see the negative modes of Southern Annular Mode, which is basically high pressure over the subpolar latitudes and low pressure over the mid latitudes. So when we have high pressure and over the subpolar latitudes, there's a tendency of weakening of the ferrule cell, and there is large interaction between atmospheric mass happening between the polar and the mid latitudes. So when this happens, what we see is that the Southern Annular Mode is correlated with the Elnino Modoki index. Further, we also see for the period 1983 to 2013 that February-March Southern Annular Mode is positively, which we have already seen correlated. It is inversely related to the falling, that is JJS Elnino Modoki index. Further, there is already a study which has already said that once we have warming over the Central Pacific, it leads to poor monsoon rainfall over the Indian region. So accordingly, for the period, we see that Elnino Modoki index versus ISMR, it gives an inverse correlation. So coming to the physical mechanism, how this is done, first what we see is the ocean part of it, wherein a simple correlation analysis, a spatial map shows that we have negative inverse correlations over the central Pacific, which starts from February, March, and it sustains itself up till JJS, the falling JJS. So is it coming from the atmospheric component, that is an inverse correlation between SAM and temperatures at 1000 HPA from February, March, evolving along the seasons till the falling JJS. So seeing the ocean atmosphere, when we take the composites of negative modes of February, March, SEM, we see that the westerlies to the west of Pacific and easterlies to the east of equatorial Pacific converging towards the central Pacific, which is the warmed up region. So how is this possible that the signal coming from the subpolar latitudes towards the tropical equatorial Pacific? So to do this, what we have done is then we have taken the meridional circulation for the composites of negative modes of February, March, SEM over the central Pacific region. And we do see that the subpolar high and the mid-latitude low, there's a propagation of the signal coming towards the mid-latitudes. Also, but let me say that it is associated with the warm SSTs of the central Pacific. So together, SAM and the SAM signals and the SST modes over the Pacific together play a role for determining the shape of the ISMR, or the monsoon rainfall over major parts of India. So when we take a Walker circulation and anomalous Walker circulation for the composites of negative modes of SAM, we see clearly the ascending mode over the warmed region, Central Pacific region, with a descending node over the Indian longitudes. So basically, we infer from this study is that when we have a negative phase of February, March southern annular mode, it gives rise to an anomalous meridional circulation in a longitudinally locked air, atmosphere, and ocean system over the Central Pacific that persists up till the falling summer, and which then propagates towards the equatorial latitudes. So this phenomenon is associated with warming of the Central Pacific, which simultaneously weaken the summer monsoon rainfall over the Indian region. So this largely, the southern annular mode largely explains the variability of monsoon rainfall over the Indian mainland. However, we would like to know what are the drivers for the Northeast Indian region. So that for that we see how the northern annular mode or the Arctic Oscillation play a role in giving us the signal over the Northeast India. Eurasian snow monsoon rainfall. Eurasian basically region has been, the snow over Eurasia has been seen to be correlated with not only with monsoon rainfall over India, but also over East Asia, Korea, Japan, and to a large extent over North China as well. So here what in the study we see is that how Eurasia in the winter, in the month of winter, especially January, has an impact over the northeast summer monsoon rainfall over India. We see an inverse correlation coming from for the January Eurasian snow with that of the falling JJS northeast rainfall. Similarly, Eurasian snow in the month of Jan with that of Atlantic SST shows an inverse correlation, and Atlantic SSTs, the summer monsoon, for the JJS season, with that of with the Northeast Indian summer monsoon rainfall, there's a simultaneous positive correlation. So when we take these regions of interest, as seen over here, and try to formulate an hypothesis, we come with a hypothesis which states that when we have an excess snow in the month of January, that is the wintertime excess snow, it leads to the negative mode of Arctic oscillation in winter. So that gives rise to meridional breaking of the feral cell, and it causes anomalous descending mode over the tropical North Atlantic, leading to high pressure area over this region. Cold SSTs which are present over during the JJS season, it persists, and it leads to zonally cooling of the northeast region through the zonal circulation. So that results in lesser Northeast Indian summer monsoon rainfall. So how this hypothesis is proved, it's shown in the following slides. Also, there has been study by Deepa which states that reduction in sea ice cover over the Arctic has increased the heat flux over the ocean in ocean to atmosphere in autumn and early winter. So this sea ice decline further gives rise to increase in snow ice, snow cover over Eurasia, leading to frequent patterns of negative mode of Arctic oscillation. So how this Arctic oscillation is impacting or trying to act as a bridge for the anomalies over snow to the SST patterns and that of any Northeast Indian summer monsoon rainfall is what we're going to see now. So the geopotential patterns for different seasons, we see that it is dominant over the winter season. So the winter Arctic oscillation is what is the main dominant mode of variability, which we're going to see. So first and foremost, we see whether the Eurasian snow has got, what happens to Eurasian snow and the temperature. So excess of Eurasian snow leads to cooling of the temperature, which is quite obvious. And that's what we get to see. Further, the winter snow is also associated with the negative modes of Arctic oscillation. So together, when we have a negative, so the composites of Arctic oscillation, the negative modes of Arctic oscillation, we have a subpolar high and a mid-latitude low, which when we average over the tropical longitudes, that is 60 west to 10 east, we see a descending mode over 20 northern tropical Atlantic. So further, we see whether what's the role of the SSTs and the Arctic oscillation in driving these modes. We see a correlation coming from the SSTs over the tropical North Atlantic along with the snow. We see that there is a negative correlation in the month of, inverse correlation in the month of January. And now when we take an autocorrelation of January SSTs over the same area of tropical North Atlantic, the correlations sustain itself up till the following summer. So together, when we see what is the vertical velocity, the zonal circulation coming from the tropical North Atlantic region towards the Northeast Indian region, we see that basically there is a descending mode over the Northeast Indian region. So the composites of Northeast region over India for the modes of Eurasia, negative modes of Eurasian snow gives this kind of a negative below normal monsoon rainfall over the Northeast India. So from the study, what we see is that the summer monsoon rainfall over India has distinct patterns over the Indian mainland and over the Northeast Indian region. While the Indian mainland region, the rainfall variability is largely explained by the southern annular mode. It's the Arctic oscillation snow and the North Atlantic SSTs, which drive the summer monsoon rainfall over the Northeast Indian region. So with this, and this work has been published both for southern annular mode and the Arctic oscillation in climate dynamics. So I end my talk. Thank you so much for your attention.
Thank you, Amida. Since time is exceeding, we will just move to the next talk, and Dr. Sourav will convene the next three talks. So Sourav, can you please?
Yeah, can you hear me?
Yes, yes.
Yeah, thank you, Dr. Suchithra. So next on the list is Dr. Aryan Pirick, who is a postdoc fellow at Monash, Australia. She works on coupled ocean atmosphere sea ice interactions across the southern hemisphere. And she'll be talking about projected impacts of Antarctic meltwater anomalies over 21st century. Over to you, Dr. Aryan.
Thank you. Could I just ask you to unshare your screen first so I can share mine?
Yeah, Dr. Amita, if you can please unshare the screen. Dr. Amita, are you there? Okay, let me see if I can.
Let's see.
Okay, thank you.
Yeah.
Okay, have you got my screen now?
Yeah, I got it.
Great. Okay, so hi everyone. Today or this evening, I'm going to be talking about a project looking at the impacts of Antarctic meltwater anomalies over the 21st century. And this is work that I've undertaken with Matt England. And so in this study, we're interested in looking at the climate impacts in simulations with additional meltwater around the Antarctic margins. And while many of these impacts will be focused in the high latitudes, we also find important changes in the tropics. And so I'll be discussing these as well today. And the motivation for this work is that the Southern Ocean surface has been observed to have freshened over recent decades, as shown in the plot here by Dirac and Weifels. And surface freshening is projected to continue over the 21st century, in particular as Antarctic ice sheet and shelves accelerate in their melting. However, Antarctic ice sheets and ice shelves are not represented in coupled climate models, and this constitutes a fundamental challenge in projecting high latitude climate change. Surface freshening of the Southern Ocean is important because of the stratification effects that it can have. So under the mean state, the Southern Ocean has cool and fresh water at the surface and warm salty water at depth, and there is mixing in between. Increased ice sheet and ice shelf melt freshens the surface and leads to an increased stratification. This reduces the convective overturning and leads to a weaker entrainment of warm subsurface waters to the surface, resulting in a surface cooling and a warming at depth. This has been shown in previous studies. So in this influential study by Bronsaler et al., they looked at the climate impacts resulting from Antarctic meltwater anomalies added around the Antarctic margins over the 21st century. And you can see in this map on the right that there's a strong cooling that occurs in response to the meltwater additions in their simulations. There's a particularly strong cooling at the Southern Hemisphere extratropics, but they found cooling extending throughout the Northern Hemisphere as well. And in addition to these changes in surface temperature, there are also other climatic effects. If you look at the magnitudes of these anomalies, they're close to 1 degree. And so it's really important that we're understanding how the meltwater is changing climate. However, there remains considerable uncertainty in projected Antarctic meltwater amounts. And this is noteworthy in this context because the Bronsaler et al. Study applied meltwater additions corresponding to the Deconto and Pollard projections, which are generally considered a very high-end Antarctic meltwater scenario. And so it's important to understand what sort of climate impacts might result from lower Antarctic meltwater additions as well. In this study, we use Access ESM 1.5, which is one of the Australian models participating in CMIP6, to investigate global climate responses to Antarctic meltwater additions over 2000 to 2100. We run 2 ensembles of 5 members each under historical and SSP 585 forcings. So they also have increasing greenhouse gases, as well as other anthropogenic forcings. And we add additional meltwater around the Antarctic coast. Access ESM 1.5 already simulates some Antarctic runoff. The model maintains a water balance, so excess precipitation over the Antarctic continent is runoff at the coast as liquid runoff. And this increases over the 21st century because as the atmosphere warms, it can hold more and it snows more over the Antarctic continent. And so we take this amount into account so that we're not double counting it in our simulations, which we designed to align with projected meltwater amounts. Our first ensemble of runs is Antarctic meltwater low. And in these runs, we linearly increase meltwater additions to 1850 gigatons per year by 2100 to make a total of 5,600 gigatons per year by 2100 entering the Southern Ocean. And this is in line with the Golech et al. Projections. And our second ensemble of runs is the Antarctic meltwater high ensemble, where we linearly increase meltwater to 13,600 gigatons per year by 2100 to make a total of 17,000 gigatons per year by 2100 entering the Southern Ocean. So this is in line with the Deconto and Pollard projections and what was used in the Bronsaler et al. Study. And you can see that we're adding vastly different meltwater amounts in our 2 ensembles. About 7 times more meltwater is being added in our meltwater high ensemble compared to our meltwater low ensemble. And we compare our output to the historical and SSP 585 experiments from Access ESM 1.5. I'll refer to these as the control, but it's important to note that they're a control with climate change. We look now at the results from our simulations. In all of the maps I'll be showing, I'll show the meltwater low minus the control anomalies on the top map, and the meltwater high minus the control anomalies on the bottom map. And I'll be presenting anomalies from 2081 to 2100. So, excuse me, first showing sea surface salinity anomalies to contrast the freshening in the two different ensembles. We see a modest freshening in our meltwater low ensemble and a very clear freshening in our meltwater high ensemble, because we're adding a lot more meltwater around the Antarctic margins. By the mechanism that I described previously, we see a surface cooling in both of our ensembles, with the magnitude of cooling strongly dependent on the amount of meltwater applied. So in our meltwater low ensemble, we see a southern hemisphere extratropical cooling anomaly of about 0.2 degrees relative to the control with climate change, but without meltwater additions. And so this corresponds to a 7% reduction in warming over the 21st century relative to the control. In our high meltwater ensemble, we're showing a 25% reduction in warming relative to the control over the 21st century. So this is really substantial. And we also see a significant reduction in warming in the tropics. In our meltwater low ensemble, we don't see this significant response in the tropics. And so this is one of the important findings of our study, that the tropical and northern hemisphere responses depend on the amount of meltwater being applied in the simulations. When we look at anomalies in sea ice concentration, we see that these largely reflect the surface temperature responses. We see a modest reduction in sea ice loss in our meltwater low ensemble and a strong reduction in sea ice loss in our high meltwater ensemble. If we next turn to precipitation, we can also see some coherent regional changes. We see a significant reduction in precipitation across the Southern Ocean in our meltwater high ensemble, and this is in response to the strong cooling, leading to less evaporation in this region and thus less precipitation. We also see a clear northward shift in the ITCZ in our high meltwater ensemble, and we do see this also in our low meltwater ensemble, although it's weaker and largely lacks regional significance. These changes in global precipitation were also found in Bronsaler et al., and we expect them because of the changes in surface temperature. When we add meltwater additions around the Antarctic margins, we cool the southern hemisphere more than the northern hemisphere, and thus we increase the temperature difference across the hemispheres. To maintain an energy balance in the atmosphere, precipitation shifts towards the warmer hemisphere, in this case, the northern hemisphere. And so we see more precipitation in the northern hemisphere. This is most pronounced in the ITCZ region. If we look at the relationship between the hemispheric temperature difference shown on the y-axis, so this is northern hemisphere temperature minus southern hemisphere temperature, and hemispheric precipitation difference shown on the y-axis, northern hemisphere precip minus southern hemisphere precip, we can see that there's a strong inter-member relationship, so a strong linear relationship across our members. Orange shows the control runs with climate change, but no increasing meltwater. Blue shows our meltwater low ensemble, and purple shows our meltwater high ensemble. And so when we add more meltwater in our runs, we further increase the temperature difference across the hemispheres because we're cooling the southern hemisphere more, and we thus have a larger precipitation difference. And the key point here is that it's important that we understand how precipitation is going to change over the 21st century. And we can see that meltwater additions around the Antarctic margins have an important influence on precipitation, and to constrain what sort of precipitation changes will occur in response to this these meltwater additions, we really need to understand how much meltwater will be entering the Southern Ocean. Will it be a lot, leading to a large surface cooling and a large precip shift, or a more modest amount? And finally, I also present 2,000 metre depth temperature anomalies at the end of the 21st century to highlight really that the surface cooling that we see, and I showed on the previous slide, is balanced by subsurface warming. In our meltwater low ensemble, we see a 15% increase in the warming at 2,000 metres above that shown by the control runs under climate change alone. Under our meltwater high ensemble, we see a 40% increase in the warming of the Southern Ocean above that simulated under climate change alone. And we also see statistically significant warming throughout the global oceans in all regions except for the Arctic Ocean, due to a shutdown in the formation of Antarctic bottom water in this high meltwater ensemble. So to conclude, our high meltwater simulations produce anomalous surface cooling, reduced sea ice loss, and ocean warming at depth. Hemispheric differences in precipitation occur in response to the changed surface temperature gradient. Our low meltwater simulations suggest that the magnitude of climate responses are strongly dependent on the applied meltwater amount. These highlight the importance of, firstly, constraining projections of Antarctic ice sheet and ice shelf melt, and secondly, of representing Antarctic meltwater in coupled climate model simulations to better project global surface climate changes over the 21st century. Thanks.
Thank you, Dr. Aryan. I don't see any question, but I have one if I can ask.
Yeah, sure.
Just on the last slide where you showed the 2000 meter depth temperature changes. So the maximum response is in, I see in the Atlantic Ocean. Is there any particular reasons for that?
Sorry, I was trying to share it, but it's not coming up again. I expect this is due to the deep water formation or the shutdown of the deep water formation in this model. So the excessive freshwater shuts down the formation of Antarctic bottom water, and I guess this is probably most pronounced in the Atlantic basin in this model.
So, and if you change the time scale, like if you look at the longer runs, do you expect that signal will, like through ocean circulation, will reflect in other ocean basins as well?
I'm not sure actually. I think the shutdown of Antarctic bottom water occurs around mid-century, so there are a few decades for it to adjust. Yeah, I'm not sure, but thank you for the question.
But I have maybe one or two more questions for you.
Okay.
I mean, this is from the attendees. What potential would you say there is for narrowing the range of uncertainty in meltwater rate changes under climate change?
Oh, that's a good question. That's really not my area of expertise. So I will, I'm not an ice sheet expert, so I would have to leave it to them.
Okay, and another one is there. Did you investigate whether it is a threshold response or a linear one to freshwater input?
Oh, that's a good question. You get it's a nonlinear response to the amount of freshwater that's added. So the more freshwater that gets added, you eventually sort of have diminishing climate effects. Once the ocean is very strongly stratified, adding more freshwater has less and less of an influence. But some of the other relationships are more linear. So if you look at, for example, the relationship that I showed between temperature differences and precip differences, they're more linear. But then the relationship between the actual amount of freshwater that's been added and temperature, say, that's not linear.
Right. So thank you for your answers and also the nice presentation.
Yeah. Thank you.
Yeah, thank you. So next we have Dr. Holly Iris. She's a postdoc at the University of Reading, working on polynyas and how the polynyas in the Weddell Sea and how the atmosphere and ocean responds to it. And in line with that, she will be talking about atmospheric response to the Weddell Sea polynya and the importance of model resolution. Over to you, Dr. Holly.
Brilliant, thank you. Can everyone see my screen and hear me okay?
Yeah.
Brilliant, thank you. Yes, hello everyone, and thank you all for coming along. So this is work I have been doing at the University of Reading with Deepa, Malin Orlen, Wunson Park, and Joachim Jensen, who are based at GMR as part of the European SOCHIC project. So a little bit of information about the polynya to start with. So starting with the very basics, a polynya is an opening in sea ice, so a small region of sea ice loss. With similar kind of ocean air fluxes to large-scale sea ice loss, but in this case enhanced with a region of deep warm water upwelling to the surface, so formed primarily from deep convection over the moored rise, amongst a mix of other ocean and atmospheric mechanisms. The Weddell Sea polynya has only been observed twice in satellite history. So once in the 1970s, or consecutively over the 1970s, and again in 2016, 2017, but this was much smaller. So most studies out there focus on what causes the polynya, both atmosphere and ocean. So we're interested on the polynya's impact on the local and the global climate. So my results will be from mostly from this AGCM experiment. They're still fairly preliminary for the response to the polynya. So the first order response, but also focusing on differences in model resolution and different models. So we've run low and high resolution simulations using free models. So our own mini MIP, HadGem3, ECM5, and OpenIFS. For HadGem and OpenIFS, these were extremes in resolution. So the very high resolution for the high, and fairly standard for low resolutions, about 100 kilometer low resolution versions of the models. ECM kind of in between, much lower resolution for the low, and the high resolution was kind of mid-resolution compared to the other two. The low resolution models were run with 100 members, and the high resolution were run with 30, which we would like to have done more, but these are very high resolution models, as I say, so they're very computationally expensive, and these are sourced with sea ice and SSTs from the 1974 polynya, which, although is less likely in future scenarios, they provide a strong maximum forcing for us to work with. So the response to the polynya, and the figures I'll show from this point onwards, so is the anomaly, is calculated as the 1974 polynya condition scenario, minus a masked non-polynya control over the region using an average of 1980s to 2015 data. So where there were no polynya, and as you can see, it's a nice clear regional forcing. So most of the results I will show are low resolution, as not all the high resolution results have been finished, although I will touch upon that a little bit later in this talk. So these are August to November across the screen. Polynya mumps, HadGem, ECM, and OpenIFS going down the screen, with hatching marking these significant regions. And so this is turbulent heat flux, which is positive in the upward, so ocean to atmosphere direction. And the first thing to notice is the locality of the response. So they're all fairly similar. And also they only have kind of small differences between them in shape, and they generally decrease in magnitude as we go into austral summer. So as we would expect, no big major results here. There are only small differences at this point between the models, notably that HadGem reduces its response quicker than the other models, and OpenIFS has a slightly larger response, and these are suspected to potentially be due to differences in interpolating, or possibly some differences between model time steps, but overall it's all within what we might expect. Surface temperatures correlate to heat flux in that they follow the same trends with time and are locally confined. However, you will notice that temperature does also increase in the region surrounding the polynya, as the north and the east, downwind at the warning, but it's still very much local and confined to this region. Precipitation follows a similar pattern with similar differences in HadGem and OpenIFS, but notably the region of significance is even smaller as we start to see a little bit more background noise there. And we also kind of get this odd significant decrease early in October for HadGem as well. However, going into mean sea level pressure, we get something, but it's no longer significant. But I wanted to include it anyway, because there's clearly something happening, a decrease in pressure, specifically of the polynya, but at the moment it's just too noisy. So I think we might need more members, which of course is possible with the low resolution. They're nice and easy to run, but the high resolution, maybe not. So potentially a problem there, or perhaps we could just say that the response is too small in comparison to noise. However, in OpenIFS, we do get a significant meridional wind response that is associated with this kind of pressure change in September. So that's something, despite both the meridional and zonal wind fields starting to show a lot of noise there. So the zonal mean temperatures response, so this is above the Polynya, Hadgem, ECAM, and OpenIFS going across the page this time. So all show a similar response between each other. They are confined to the lower troposphere, but with a small significant response aloft. And I call this pattern a warming bubble with a chimney. But they're all nice and similar, which is a good sign. And even for the zonal wind here, so the response is quite messy in all the other months, but September, basically it shows some good agreement and significance, I would say, with a weakening both south and north in the coastal easterly and the westerly jet respectively. So remember that that increase to the south is actually a decrease because it's zonal wind. I'll also mention, although not shown, that currently our high resolution versions don't really agree with each other, but as I said, we still need to finish running them. So maybe with a few more members, we might get some more agreement. So my final slide, a quick comparison of the resolution. So this is with Hadgem, and the timing and spatial extent is very similar, but the most striking thing here is the magnitude nearly doubles with resolution. And this surprised us because, we found the sensible to latent heat ratio flux was the same, well, as it should be. It is just a lot higher in the high resolution. We have whittled it down to potentially wind stress component of heat flux, and that's something we're currently looking into. But we thought this was a really interesting result, especially as recent paper Straffing et al. 2021 that looks at regional Arctic sea ice tends to see not much of a difference between resolutions. So we found this quite interesting. But yeah, we're looking into this further. And remember that in the low resolution, OpenIFS also gave us a slightly bigger response, and that was a slightly higher resolution again. So possibly something interesting there to talk about, maybe, and when we look at the dynamic response, we again find even greater differences. So it's at the moment, it's still very much preliminary. There's a lot of interesting initial work going on here, but generally we find that the models between themselves, they're consistent-ish across similar resolutions for temperature, precipitation, etc. And then mostly for September when you go into the dynamic response. The resolution and models make a big difference in the dynamic response, so pressure and wind, which is small in comparison to noise. Resolution makes very little difference in the initial surface response, but does give a larger magnitude. So the spatial response is similar, but the magnitude is not. Other studies have shown that there could be potentially larger impacts for the Weddell Sea Polynya, and I think our work shows that, this just being the first order response, those other models and studies may rely on secondary feedbacks, for example, from coupling. Which leads on to our future work. So to start with, why the resolutions are behaving differently. A comparison with a coupled model that is currently being run and set up by Mullen. She is currently working hard on that at GMO, and then we're also going to be doing a primavera analysis of the Polynya, so looking at how resolution impacts both the ocean and the atmosphere, how in primavera it affects the formation of the Polynya and the kind of interactions with the Polynya. So yeah, that's everything. Thank you very much.
Yeah, thank you, Dr. Hoji. I don't see any questions so far, but we have some time, so people may give us some questions at the end of all the talks. So yeah, thank you, Dr. Hoji. So next we have Swati. Swati is from NCPR. She will be talking about the spatiotemporal variations and trends of Antarctic sea ice from 1979 to 2020. Over to you, Shwati.
Hello everyone, my name is Swati. It's nice to meet you all, and I'll be presenting on spatio-temporal variations and trends of Antarctic sea ice from 1979 to 2020. So as we can see, Antarctic sea ice has great implications and importance on global climate system because it is very crucial as it modifies the heat, momentum, and energy transfer from ocean to atmosphere. It is also very sensitive to climate change, and it's provide early signals of climate change. It also influences regional and global climate variability through a mechanism called ice albedo feedback. So Antarctic sea ice, we have divided into 5 sectors, and the sea ice variability and mechanisms in each of these 5 sectors are very unique. So our aim and objective of this study is to analyze the decadal, monthly, as well as seasonal sea ice changes and analyze the relationship between SST, sea surface temperature, 2-meter air temperature, and sea ice. The data sets we have used here is passive microwave satellite data of 42 years from 1979 to 2020. Sea ice concentration data has been derived from NASA team algorithm NSIDC, and SST and 2-meter air temperature data has been derived from ERA5. So here we have presented the time series graph of monthly average, monthly deviations, annual and seasonal averages of sea ice extent. And here on the box, it's the slope per year and slope per decade percentage of annual as well as the 4 seasons. So here we can see that the sea ice is clearly showing a seasonal trend, and the maximum or the average summer sea ice extent is around 3 million square kilometers, usually around February, and maximum or average winter sea ice extent is around 19 million square kilometers. As we can see here, the sea ice trend in Antarctica was showing a clear positive trend till 2015, and after 2015 there has been an unprecedented decline. So the maximum recorded sea ice extent was obtained in the month of September in 2014, and record minimum sea ice extent has been obtained in the year of 2018, just nearly 3 years after the record maximum. So this is what making Antarctica sea ice studies curious. So we have taken annual and 4-season spatial as well as temporal time series studies. So this is the annual time series. Here we can see that the Antarctic sea ice is showing a positive trend over the last 42 years, while AT is showing a slight negative. SSC is also showing a slight positive trend. If you look at the spatial trends, we can see that the area of Ross and Amundsen Sea is showing a negative sea ice concentration anomaly, while areas of Weddell Sea and Bellingshausen and Atlantic Peninsula and Western Pacific region are showing positive sea ice concentration. In the case of SST, it's clear that there is an asymmetry between East and Western Southern Ocean. The Eastern Southern Ocean is showing a positive SST, while the Western Southern Ocean is showing a cooling effect. Same in the case of 2-meter air temperature, there is a warming over the Antarctic landmass compared to the surrounding Southern Ocean, and warming is prominent over the Ross Sea sector. If we look at the summer temporal or spatial trends, it can be seen that in summer the trend is almost constant over the last 42 years, while there is a slight negative trend in case of SST and AT. In case of sea ice concentration, it is clear that there is a clear increase in sea ice or positive anomaly in sea ice concentration, which is seen in the Weddell sea ice sector, and there is a negative anomalies seen in the Ross Sea sector closer to the coast. And in case of SST, there is warming in Rossy sector and cooling in the western or Antarctic Peninsula region. The mechanism or the mechanism involved in this sector, it can be seen that the positive sea ice anomalies in Weddell Sea sector has been attributed to a mechanism called spring intensification, which persists till autumn. This results in the intensification of Weddell Gyre and causes a westward advection of sea ice. While on the other hand, the Amundsen Sea, there is a warm air advection from the tropic towards the polar region, which in turn heats up the Antarctic landmass, which causes a reduce in sea ice here. In case of autumn, we can see that there is an overall positive sea ice concentration anomaly or positive sea ice concentration trend in autumn, while SST is showing a negative trend. In case of the spatial trend, SIC is again showing a positive trend over the northern region of Weddell Sea sector, while in Amundsen and Rossy sector, there is a negative sea ice anomaly. And we can see that 2 meter air temperature is showing significant warming in Ross ice shelf and Weddell Polynya region and cooling over Western Pacific and Indian Ocean regions. This can be attributed to the fact that a major sea ice increase shown in Weddell Sea sector can be due to the advancement of sea ice along with the westerlies during the autumn season. The decrease in ABS sea ice has been attributed to the fact that advection of warm air from warm and moist air from the tropics and accumulation here in the Antarctic landmass region and resulting in the melting of sea ice. In case of winter, it is again prominent. There is a clear positive trend in sea ice concentration, while SST and AT is showing almost constant over the last 42 years. There has been a substantial increase in SST after 2015, and negative sea ice concentration is seen in Indian Ocean, and positive sea ice concentration is seen in ABS or Amundsen-Bellinghausen Sea sector and some regions of Western Pacific region. In case of sea surface temperature, there is a cooling effect over mainly concentrated in the Western Southern Ocean region, and some heating is seen in the Western Pacific Ocean region. In case of 2 meter air temperature, there is a significant warming over the Antarctic landmass, again concentrated on the Indian Ocean region and Ross Sea sector. The mechanism involved, it can be due to during cold seasons, surface heat flux is directed from the ocean to the atmosphere, which results in the cooling of sea surface, creating an ideal environment for the formation of sea ice. A strong cooling in winter season results in higher negative sea ice concentration and AT relationships. The Indian Ocean sector is also well known for the formation of bottom water region and brine rejection. The zonal wave 3 induces an uneven distribution in the uneven distribution of energy in the Antarctic sea ice region and is reflected in the sea ice concentration, growth and spread. Next is the spring season. Here we can see that there is a positive trend in sea ice, but what prominent is here is a significant positive trend in atmospheric temperature anomaly, while SST anomaly is almost constant. And in case of sea ice concentration spatial trend, we can see that the magnitude, even though it is positive, the magnitude is considerably decreasing, which indicates the onset of melt season. Here again in Weddell Sea, there is a positive sea ice concentration anomaly, and in Western Pacific Ocean region, there is also positive sea ice concentration anomaly. And in case of SST, there displays a dipole where heating is observed on the eastern side of Antarctica and cooling effect is seen on the western side of Southern Ocean. And in case of 2 meter air temperature, what's peculiar is that there is a significant warming over the Antarctic landmass region. SIC exhibits positive correlations along the coastlines, but there is a decrease in magnitude. AT anomaly is mostly positive, except for Bellinghausen Sea and west of Weddell Sea and Western Pacific Ocean. These changes are linked to zonal wind changes, where SAM is also the strongest during spring along with the autumn. This can be the reason for this sea ice formation.
Swati, can you please speed up?
Yes. Seasonal sea ice variability and connections. It can be explained using the Ekman divergence model. Cyclonic wind in the Southern Ocean causes Ekman divergence of sea ice, thus creating an open water called leads. During winter months, these leads helps in the formation of freshly formed ice, which enables the sea ice to form in the interior rather than the periphery. And during summer seasons, it open spaces absorb the incoming solar radiation and melts the sea ice from below. And there are some reasons that are proposed for the decline of sea ice of 2016 are strong northerly warm airflow, SAM, and Elnino conditions, and strong presence of zonal wave 3 around Antarctica. Thank you.
Okay, thank you, Swati. May I request Deepa to take over from now?
Yeah, thank you, Dr. Sourav. Myself, Deepa. I am from Florida Agriculture and Mechanical University. I am convening the remaining session. I think we are running a few minutes late, so let us move directly to the session. Our next speaker is Dr. Avinash Kumar from National Center for Polar and Ocean Research, India. He talks about the rapid sea ice changes and variability in the Weddell Sea. Let us welcome him. I think he has a pre-recorded presentation. Can you please share his presentation?
Hello everyone, greetings from India. I am Avinash Kumar from National Center for Polar and Ocean Research, NCPOR, is here to present on rapid sea ice change and variability in the Weddell Sea, Western Antarctica. Before I talk in details about the Weddell Sea, I would like to brief about the total Antarctica. Here from the graph, we can see the changes in Antarctic sea ice during annual summer and winter period. It clearly shows that Antarctic sea ice is gradually increasing since the satellite era started. However, the sudden decline in Antarctic sea ice from 2016 onwards has been recorded in seasonal and interannual scale. In the top left panel, you can see that spatial plot showing the summer and winter sea ice concentration of Weddell Sea, where we see that differences between summer and winter is very huge. So this is my outline of my talk. I will be going to cover the sea ice variability in Weddell Sea sector, their influence of ocean atmospheric interaction on the sea ice variability, and finally I will be going to conclude about the variability of ocean atmospheric forcing during high sea ice years. As we have seen the first slide, that sea ice in the Weddell Sea is showing contrasting change between the summer and winter season. Here we have a plot where we can see that how the monthly sea ice extent is varying in the Weddell Sea, which is shows this is the lowest which has record has been done in summer. It is in summer month of February, whereas the highest record it is in September, where we can see the summer and winter has a huge difference. Almost 4 to 5 million square kilometer variation has been recorded in the Weddell Sea. However, the figure C and D, it shows the annual and the 4 other seasons how the sea ice extent variability has been done. Over the 41 years when we have calculated, analyzed the trend, it has shown that annual sea ice of Weddell Sea is showing the positive trend, whereas the austral summer, especially the summer which is having significant positive trends, has been recorded, whereas the spring and austral winter has a negative trends. When we talk about the overall of the 41 years, the analysis reveals that annual sea ice extent was increased about 21% from the record minimum, which was 1999, and to the maximum record of 2015, whereas it has been dramatically declined by 20% between the 2015 and 2019. Now I will be going to talk about the influence of ocean-atmospheric interaction on seasonal sea ice variability. The map shows the 41-year trends analysis of sea ice concentration, sea surface temperature, zonal wind, and wind speed. Weddell Sea is having a unique geographical location, and one such important aspect is location of Antarctic Peninsula that act as a barrier. Over the last 4 decades, the austral summer results a significant increase in the eastward, especially towards the western region of below the 60 degrees, and decrease in sea ice concentration in the western of Antarctic Peninsula in the western in Weddell Sea. The significant changes in sea surface temperature are showing a strong inverse relationship with the sea ice variability in the Weddell Sea and Western Peninsula. The remarkable intensification has been observed, the intensification of westerlies and increase in wind velocity and lower latitude, especially in the 55 degree to south to 50 degree, resulting a higher sea ice concentration towards the north of 65 degree. However, the increase in sea ice concentration toward the south of 65 degrees south is resulting of a poleward shifting of westerlies, leading a strengthening of Weddell Gyre. The Weddell Gyre also it is associated with the cooler sea surface temperature within the gyre and warming SST towards in the north lower latitudes. Now we will be moving what the next season is autumn. This autumn in the sea ice concentration trend shows a significant increase in the eastern Weddell Sea. The positive sea ice concentration trend is well linked with the negative sea ice trend. The season recorded a decrease in latitudinal sea surface temperature differences and weakening of westerlies, resulting in movement of northerly wind towards the pole and weakening of Weddell Gyre. The enhancement of northerly wind accelerating loss of sea ice is associated with warmer water influence in the western Weddell Sea. Besides the Weddell Sea gyre, promotes the advection of sea ice towards the eastern Weddell Sea and thus contributing a substantial sea ice growth. However, we observe that northward equant transport is taking place that leading to the warmer water and upwelling. The increase in the coastal sea ice may be linked with the convergence of wind resulting in piling of sea ice which has been observed. However, very interestingly, we see that in the sea ice concentration increase in the coastal region during the winter and a significant decrease in sea ice concentration towards the north of the 65 degrees that occurs during the austral winter. However, the sea surface temperature is low, especially south of the 65 degree and north of the 65 degree, and high north of the 65 degree. It has been also noticed that westerlies are weakening, thereby accelerating the intensity of wind from the north and northwest region. The shifting of wind direction result in weakening of Weddell Gyre, where it is associated with the upwelling and warming waters transport from the Atlantic region. Thus, the process resulted the significant decline in sea ice concentration in most of the region of the Weddell Sea. However, in such coastal regions which are likely to be affected by eastern and gravity-driven winds over the Antarctica, a significant positive trend has been reported. Next, in the last season, which is the spring, where we have seen that the spring, the sea ice concentration was declined at accelerated rate. The sea surface temperature was positive toward the eastern Weddell Sea. The zonal wind pattern also it is forming as a dipole structure, where the intensification of wind is started and westerlies intensification and easterlies intensification takes place during this season. The wind intensification leads to strengthening of Weddell Gyre that increases the transport of cooler surface water along the coastal region of the sector. However, the decrease in sea ice concentration is due to the Weddell Gyre that results in cooling towards Antarctic coast and warming towards the North Gyre. Overall, when we look about that, seasonal sea ice concentration variation in Weddell Sea Gyre are largely associated with the longitudinal thermal differences and westerlies intensification, which culminating in the weakening and strengthening of Weddell Gyre. Now we will be going to talk about that the final concluding part of this talk about the composite analysis. It is very important to understand that which forcing is more dominant in the seasonal sea ice variation. Therefore, we have analyzed the composite difference of net heat flux and sea surface temperature based on sea ice years, high sea ice year, especially ice years. The result shows that primary force is resulting in austral summer and spring sea ice variability is oceanic heating. However, the autumn and winter sea ice is influenced by both ocean and atmospheric forcing. So this is the entire conclusion, which is the ocean and atmosphere is working in the different season and the working different season in the Weddell Sea Gyre. So this was my end of talk, and thank you so much for your kind attention. And if any queries and questions, suggestions, please write your questions. I will be happy to discuss and give your answer. And I'm extremely sorry I was not sure that I will be going to attend this conference because I was completely busy in the arrangement of this SCA as a member of LOC from India. So thank you so much. If any queries, I will let you know. Very good, very soon. Thank you so much. Have a nice day.
Thank you, Dr. Avinash Kumar. Our next talk is on Dr. Meera Nair from SRM University, Chennai. She talks on quantifying CMIP6 epistemic uncertainty in AOT projects over Antarctica. Let us welcome Dr. Meera.
Ma'am, greetings to all. Am I audible, ma'am?
Yeah, you are. Yeah, we can hear you. Yeah.
Okay. So, ma'am, greetings to all. Aerosols, as we know, aerosols continue to contribute the greatest uncertainty in climate projections. It's important to quantify uncertainties. So here, our work is based on quantifying CMIP6 epistemic uncertainty in AOT projections or aerosol optical thickness projections over Antarctica. Antarctica directly influences the lives of more than half of the world's population living in coastal region. Therefore, it is highly needed to better understand and understand the past and to project its climate for future as well. Since climate models are the only tools for available for this purpose, even though climate models comes with uncertainties, they are important tools to analyze the future climate over this pristine region. So this study is an attempt to unfold the epistemic uncertainty in future climate projections over Antarctic region. The objectives of our work includes to estimate the mean change in aerosol optical thickness over Antarctica region between multimodal ensemble of CMIP6 and Mara2 data for historical time period from 1995 to 2014, and to quantify epistemic uncertainty in CMIP6 AOT projections for future scenario SSP 585 over Antarctica from 2015 to 2094. And the third objective is to estimate the signal to noise ratio from CMIP6 AOT future projections. In this study, we used aerosol optical thickness at 550 nanometer from Mara2 reanalysis data and from CMIP6 projections. We used data from 1995 to 2100 from CMIP6 projections and 1995 to 2014 data from Mara2. And we use these 5 models from CMIP6, and all model data are regridded onto a regular grid at 1 degree by 1 degree resolution. The study area of this work extends from minus 180 degree west to 180 degree east, minus 90 degree south to minus 65 degree north. Aerosols are major components affect atmospheric system. It's important to study how it is varying from region to region. So we consider the aerosol optical thickness at 550 nanometer from MERA2 as well as multimodal ensemble mean of CMIP6. And we can identify the magnitude, difference in magnitude in AOT projections from MERA2 reanalysis data as well as CMIP6 multimodal ensemble mean. We calculated the mean change between these two, MERA2 and CMIP6, and we obtained a RMSE value of 0.004. To get a better understanding about how climate models are projecting this AOT projection, we consider 5 models and we compared it with MERA2 data. And we can see from model to model, the spatial and seasonal variation of AOT varies from model to model. Here, the seasonal mean of AOT over Antarctica region from MERA2 and CMIP6 individual models are shown. In this bar plot, we can see the aerosol optical thickness from MERA2 multimodal ensemble as well as MERA2 and CMIP6 multimodal ensemble mean. Except March, April, May, for all the seasons, CMIP6 multimodal ensemble is underestimating the value of AOT, and for March, April, May, CMIP6 multimodal ensemble is overestimating to some extent. This is a global representation of aerosol optical thickness at 550 nanometer. The red dotted line represents MERA2, black dotted line represents CMIP6 multimodal ensemble, and the other 5 colors represent 5 individual models from CMIP6. We can see, except this Canada CAN ASM5 model, all models are following the trend. Even though magnitude is different, models are following the trend of AOT. But Canada ASM5 has different trend also. So from model to model, it is projecting differently. Some models are projecting well, some models are not projecting well the AOT at 550 nanometer over global scale. Coming to Antarctica region, most of the model, there we can see the MERA2 observation, the red dotted line, CMIP6 multimodal ensemble, and 5 model, how it is varying from month to month. The monthly mean over Antarctica region is shown in this figure. 5 models are giving 5 different representation, even though in some regions MERA2 and CMIP6 multimodal ensemble is showing somewhat similar result. This is to get a better picture how these models are representing season wise. We classified into 4 seasons like December, January, February, March, April, May, June, July, August, September, October, November over the Antarctica region from multimodal ensemble mean as well as MERA2. We can see December, January, February, March, April, May, June, July, August, September, October, November. Even though there are not much difference in magnitude, the spatial representation, how it is varying from CMIP6 models and MERA2 reanalysis data. So from here, we identified that there are some certain differences in the projection, in climate projections from model to model. So it is important to study why these models, why this uncertainty arises. Mainly, uncertainty in climate projections are aggregated into 3: internal variability uncertainty, epistemic uncertainty, and scenario uncertainty. In this study, we focus on epistemic uncertainty or model uncertainty. Epistemic uncertainty arises due to the imperfect knowledge about the climate system and quantified with the help of large number of climate models that simulate the future climate for the same emission scenario. We partitioned uncertainty according to along the lines of Terray and Bow, and epistemic uncertainty. We calculated epistemic uncertainty for future climate projection under SSP 585 scenario. Here we can see the equation. Epistemic uncertainty is given by multimodal mean change minus mean change projected by all realization over number of models minus 1. And we calculated the epistemic uncertainty according to this equation. And for better understanding, we quantified the uncertainty over 4 20-year future time periods like 2015 to 2034, 2035 to 2054, 2055 to 2074, 2075 to 94. Future climate projection under shared socioeconomic pathway SSP 585. Here we can see the seasonal mean of AOT at 550 nanometer for December, January, February over Antarctica region from multimodal ensemble mean of CMIP6 under SSP 585 scenario for future time periods. we can see the AOT, the seasonal mean of AOT is more in this coastal region, and the bottom row represent the epistemic uncertainty, how epistemic uncertainty is varying from if we classify this region into 4 regions, like 90 degree to 180 degree will be region 1, 180 degree to minus 90 degree is region 2, minus 90 to minus 180 is region 3, minus 180 to 90 will be region 4 for our study purpose. So region 3 will showing high uncertainty or during the time period 2015 to 35 over December, January, February. Coming to March, April, May season, the seasonal mean is represented in this top row, and we can see the coastal area is showing, the West Antarctic coastal area is showing high seasonal mean for AOT. And coming to epistemic uncertainty is also high in this coastal region, and the spatial representation is different from previous December, January, February season. And we can see during 2017 to 94, the epistemic uncertainty is high in this 3rd region. Coming to June, July, August, seasonal mean as well as epistemic uncertainty is represented in this figure. Here also we can see how epistemic uncertainty is analyzed over the Antarctic region, and coastal areas are only showing high epistemic uncertainty. This is for same for September, October, November season, seasonal mean as well as epistemic uncertainty, how it is varying from season to season. So we observed how aerosol optical thickness varies from seasonal spatial, the seasonal and spatial variations of AOT over Antarctica under the shared socioeconomic pathway 585 scenario from CMIP6 multimodal projections. And we also calculated signal to noise ratio. Signal to noise ratio is another important factor in climate projection, where signal is the amplitude of projected change and noise is the measure of uncertainty in the projection. And higher signal to noise ratio represent that the changes are large relative to variability and therefore more robust. We calculated signal to noise ratio for 4 20-year future periods, 2015 to 34, 35 to 54, 55 to 74, 75 to 94. And we observed high signal to noise ratio in June, July, August for all the season, for all the time period, from near future to far future. June, July, August season is showing high signal to noise ratio, which means the variations, the changes are more robust, and it is large, changes are large related to variability. For a better understanding, we quantified the epistemic uncertainty in 4 regions of the study area, as shown in the figure. Region 1 represent this Kemland and this region. Region 2 includes the Weddell Sea and West Antarctica region. Coming to region 3, as shown in the figure, region 3 also comes under West Antarctica region. Region 4 includes Queen Mary Land and the corresponding regions. We quantified the epistemic uncertainty over these 4 regions for 4 future time periods, like for 20-year time periods for 4 seasons. And for every time period, like 2015 to 34, we observe the highest uncertainty in region 3, which is West Antarctica region, followed by region 2. Region 2 also comes under Antarctic Peninsula region. So coming to 2035 to 54 also, we observed high uncertainty in 3rd region, followed by 2nd region. The same pattern follows for all the 20-year time periods. So it is evident from this figure that epistemic uncertainty increases over time, and it shows higher epistemic uncertainty in West Antarctica region and shows lower uncertainty in East Antarctica region. So here comes to the end of my presentation. As I mentioned earlier, uncertainties are aggregated into 3. Model uncertainty or epistemic uncertainty arises due to the imperfect knowledge or due to the lack of training data, or some models may project well, some models may not project well. So if we improve this model, we can project well. For a better understanding of future climate projection, model improvement should be done, and this uncertainty can be reduced. So it's important to study how models are projecting climate variables in different regions of the world. That's it. So in the study, we obtained UT from CMIP6 database for the period 1995 to 2100. We also used Meratu reanalysis of AUT at 550 nanometer for the period 1995 to 2014 in order to compare and quantify the uncertainty in CMIP6. And the epistemic uncertainty, signal to noise ratio, as well as mean changes in AOT are majorly addressed in our study. We estimated the mean change, and it's found that East Antarctica region shows highest mean change, and we obtained the RMSE value of 0.004 over the study area. The epistemic uncertainty is quantified for future shared socioeconomic pathway 585 scenario, and it is evident that it increases over time, and East Antarctica region shows the lowest epistemic uncertainty, and West Antarctica shows the highest uncertainty for all season. Signal to noise ratio shows the highest value for June, July, August over the study region from multimodal ensemble mean under SSP 585 scenario for future time periods. We will focus on remaining two uncertainty, like internal variability uncertainty and scenario uncertainty on future. That's it. Thank you for your attention and patience. Thank you.
Thank you, Dr. Meera. I think we don't have any questions in the chat. I got a few questions. If we have time, we can proceed with those questions.
Yes, Deepa, you can proceed.
Yeah, yeah. Yeah, I am sharing the questions I got. Can you see the screen?
Yes, we can see the screen.
Yeah, I think the first question is to Dr. Sang-Yoon from Dr. Milinsky. Do you consider impact of central tropical Pacific influence on West Antarctica, AP via teleconnections? Dr. Sang-Yoon, are you there? I think he is not there. So can we go to the next question from Dr. Sourav? Just out of curiosity, have you checked how good are those models in terms of turbulent heat fluxes in the southern hemisphere? This question was to Dr. Hollier.
Deepa, she has replied to me on chat, but if she wants to, she can, or we have time, she can also once in the public forum.
Okay, yeah.
Would you like me to answer it publicly as well?
Yeah, yeah, you can.
Yeah, so yeah, this is something that we're looking into with the wind flux. We've just had an interesting conversation now about southern hemisphere heat flux biases and how they can be different between the experiment and control, and seemingly they should be very similar. So yes, this is something that we're currently looking for, and hopefully this conversation could provide some useful information. Thanks.
Okay, thank you. Yeah, our next question is to Dr. Amita from Dr. Suchithra. Does the sea surface temperature shown in your schematic diagram has any connection with Atlantic Dipole SST? Dr. Amita?
Yeah, that's a good question. We have also checked with the Atlantic SSTs. We have seen a connection, but then it's not significant. But we have to see for in paleoclimatic studies if we can see any kind of a connection, which we propose to do this work in the future. Thank you so much for the question.
Okay, thank you, Dr. Amita. Our last question is from Dr. Thomas, British Antarctic Survey. This is to Dr. Wang. Do you have any suggestions for why the trends were stronger in autumn and winter? Dr. Wang?
Okay, I'm here. Yeah. Okay, it's a good question. And actually, in fact, this is working we are ongoing, and maybe the positive perhaps trade of some lead to this the increasing enhancements of meridional circulation traits, and but the excess mechanism is not yet clear, and in the future we would to use model or to simulation this mechanism. So so this is my answer. Okay. Mm-hmm.
Okay, thank you, Dr. Wang. Now I hand over the session to Dr. Suchithra.
Thank you, Deepa. So can you, okay. So we have reached the end of the session. So before that, I want to thank the speakers and participants for their active participation. And I hope that at least all of you got some takeaway points that will be useful for your future research by attending this session. And I take this opportunity to thank the SCAR 2022 for selecting me as the convener for this session. And I also thank Dr. Deepa and Dr. Sourav for all the support they have given. And so now we have reached the conclusion of this session. Thank you all. Bye-bye.